Vladimir Rovensky. Both of them deal with some particular cases of this general and somewhat vague problem of describing the geometric structure and trying to classify, in some cases, Euclidean submanifolds that carry totally geodesic foliations. So let us recall that a smooth foliation on a Riemannian manifold is totally geodesic if all of its leaves are totally geodesic submanifolds. This is equivalent to saying that if a geodesic of M is tangent to the foliation F at some point, then it's contained in the leaf of F through that point. So, first of all, I would like to discuss a theorem of the Hahn type which characterizes Riemannian manifolds that carry such a totally geodesic foliation, whose orthogonal distribution is integrable. First, I need to introduce the concept of a polar metric on a product manifold. So if we have a product manifold, M0 times M1, we call a metric on it polar if there exists a metric on the first factor and a smooth family of metrics on the second one, which are parameterized by the first factor, such that the metric can be written in this way. Well, the best way to understand what a polar metric is to say that a metric is polar if we require that the product foliation is an orthogonal net, which means that the slices corresponding to one factor are orthogonal to those corresponding to the other. And in addition, that the induced metrics on the slices corresponding to the first factor, say, are all the same, but no requirement for the other. So this type of metric includes the so-called quasi-warped product of metrics, which are metrics of this type in which this warping function whole may depend on both factors. The more usual warped product metrics correspond to the case in which the function whole depends only on the first factor. So a quasi-warped product metric is just a polar metric for which all the metrics on the slices corresponding to the second factor are conformal to each other. The case of warped products correspond to the homotetical hypothesis, and a product metric is just one in which all such metrics are isometric to each other. So what polar metrics have to do with totally geodesic foliations is the content of this proposition. A metric on a product manifold is polar if and only if this product net is an orthogonal net, just meaning that vectors tangent to different factors are orthogonal to each other. And in addition, the distribution of tangent spaces to the first factor is totally geodesic. So this proposition also explains the terminology, polar, for such metrics, which come from this example. If we have a Riemannian manifold, which is acted on by a closed subgroup of the isometric group, and the action is polar, and this means that there exist sections, submanifolds that intersect every orbit orthogonally. well, this condition of being polar is equivalent to the assumption that the distribution of normal spaces to the maximal dimensional orbits be integrable. And in this case, it's automatically totally geodesic. So if we fix a regular point for the action and consider the section that passes through it, we can define this map psi from the product of the section and a regular orbit into the regular part of the manifold. And this is a local diffeomorphism that maps the leaves of the product foliation of this product manifold into the leaves of the orbits and the sections. So since we know that this distribution is totally geodesic, from the previous proposition, it follows that the metric induced on this product manifold is polar. So this is just to justify the terminology polar for such metrics. So it's a natural question whether polar metrics can only arise on product manifolds. And this is the content of this, the hump type theorem. In fact, if we have a remaining manifold which carries, well, this assumption is equivalent to assuming that we have a totally geodesic foliation whose orthogonal distribution is integrable. In this situation, one can show that there exists locally and globally, in fact, if we assume the manifold to be simply connected, and it's enough to require the leaves of this totally geodesic foliation to be complete. Then we have, well, I call a product representation. This means a diffeomorphism from a product manifold into the remaining manifold M that maps the leaves of the product foliation into the leaves of E0 and E1 respectively. So an induced metric is polar. So any remaining manifold that carries a totally geodesic foliation whose orthogonal distribution is integrable is locally or globally under these assumptions a product manifold endowed with a polar metric. So now we turn into the problem of looking for Euclidean submanifolds that carry totally geodesic foliations whose orthogonal distribution is integrable. This leads us to the notion of a partial tube, which has been introduced by Carter and West in the 90s. We start with an isometric immersion with the property that its normal bundle has a parallel flat normal subbundle. Equivalently, we assume that there is an orthonormal set of parallel normal vector fields along the submanifold. So this is always satisfied, in particular if the submanifold has flat normal bundle. Then we have this vector bundle isometry between this vector subbundle and the vector subbundle is spanned by those normal vector fields, given in this way. This is a parallel vector bundle isometry. And then we consider another isometric immersion into this Euclidean space, whose dimension is the rank of the vector bundle, vector subbundle E. And then we define this new map F from the product of M0 and M1 in this way. Geometrically, what we are doing is to take a submanifold in a normal space to the former one, and then parallel transporting it along the submanifold F1 with respect to its normal connection. So this is what is called the partial tube over this submanifold, and this is the fiber. So let us see how some special classes of submanifolds fit into this notion. For instance, we can always regard products as partial tubes in this trivial way. We consider a submanifold which reduces codimension. It means that it's contained in a linear subspace of the ambient space. And then we just take as the vector subbundle E, that given by the orthogonal complement of this linear subspace into the ambient space. Then if you just take an isometric immersion into this Euclidean space, the corresponding partial tube over F1 with fiber F0 is just the ordinary product of F0 and F1. Well, a more interesting example is given by the so-called warped products of isometric immersions. In this case, we start with a submanifold that is contained in a hypersphere of some linear subspace of the ambient space. And then we take as the vector subbundle E, the one whose fiber at any point is spanned by the orthogonal complement to this affine subspace and the position vector of the original submanifold. Then we have this parallel vector bundle isometry, and we choose it in such a way that this first vector is sent into the position vector at any point. And we can define this new submanifold F in this way. So the partial tube over F1 with fiber F naught tilde. And this is what we call the warped product of F naught or F naught tilde and F1. For instance, if we start with just an umbilical inclusion of a hypersphere into Euclidean space, we get an ordinary rotational submanifold which has F naught as profile. We also get cones in this way if we just start with a submanifold with S equal to 1. And the reason these submanifolds are called warped products is that, of course, the induced metric on M naught times M1 is a warped product of the metrics G naught and G1. And this is the warping function, just like in a rotation surface. These immersions have the additional property that the second fundamental form is adapted to the product net. This means that the tangent spaces to each factor are invariant under all shape operators of the submanifold. So this can be generalized in the following way. If we have a partial tube over a submanifold F1 with fiber F naught, then the induced metric is always a polar metric. We can write down explicitly what the family of metrics G1 is. And it has the same property that the second fundamental form is adapted to the product net. Well, in the case of warped products, there is a very useful result by Nolker, which states that those two properties characterize warped products of immersions. If we have an isometric immersion of a warped product manifold whose second fundamental form is adapted to the product net, then it's a warped product of immersion. This is a very useful result we use a lot in submanifold theory. And we have what we have been able to do is to extend the theorem to the class of product manifolds endowed with polar metrics. So if we have such a product manifold, and we have an isometric immersion of it with the same assumption as in Noether's theorem on the second fundamental form, then it must be a partial tube. And we can easily derive Noether's theorem from this result if we assume in addition that the induced metric is a warped product. So we look at the theorem as a decomposition theorem for immersions from product manifolds under those two assumptions. And of course, we can look at it before that. This can also be regarded as a generalization of a former result in collaboration with Marcos and Luis, which characterizes submanifolds whose relative nullity distribution has the property that its orthogonal distribution is integral. Such a submanifold must be a generalized cylinder. A generalized cylinder is just a partial tube in which the fiber is just totally geodesic. I mean, we just take a parallel flat normal subbundle of a given subbundle, a given submanifold, and parallel translate it along the normal bundle. So, going back to the problem I stated in the beginning of the talk, we can look at the previous theorem as a result, saying that if we have a submanifold that carries a totally geodesic foliation whose orthogonal distribution is integrable, then as soon as this assumption on the second fundamental form is satisfied, it must be a partial tube. Well, it's useful to see what this theorem says for, say, surfaces in R3, or a little bit more generally, surfaces with flat normal bundle. So what it says is that if you have a surface with flat normal bundle, and we assume that the curvature lines corresponding to one of the families of curvature lines are geodesics, then it must be a partial tube. So in this case, what a partial tube means is just that you take a curve in Euclidean space, you take another curve in a fixed, affine normal space to it at a given point, and then parallel translate it along the curve with respect to the normal connection. So for a surface in R3, of course, it's an easy exercise to see that the condition for one family of curvature lines to be geodesics is that the corresponding principal curvature be constant along the curvature lines of the other principal curvature. So if you have a surface in R3 with the property that one of the principal curvatures is constant along the curvature lines corresponding to the other principal curvature, then it must be generated in this way. You take a curve, another curve in a fixed normal space to it, and parallel translate it along the normal connection of the curve. Well, so in this result, we have been able to understand what are the Euclidean submanifolds that carry a totally geodesic foliation whose orthogonal distribution is integrable. This is just another way of stating this assumption. But we have this assumption on the second fundamental form. What we will do now is to see what can be said if we skip this assumption but restrict to the case of hypersurfaces. So this is joint work with Marcos and Vladimir Hovensky. the problem is now, and they also deal only with the case of one codimensional foliations. So we want to get some classification results, then we must restrict to some particular situation. We want to understand what are all Euclidean hypersurfaces that carry a totally geodesic foliation of codimension 1. And well, we assume the leaves to be complete or not. But we don't want to add any extra requirement. So of course we have to get rid of some trivial examples before trying to get any classification result. Of course, any flat hypersurface is an example. You can take a foliation of a Euclidean space by hyperplanes and then look at an isometric immersion of it in codimension 1. Another class of also trivial examples is we just start with a surface in R3, take a one-parameter family of geodesics, and then take the product of the surface with an Euclidean factor. So we get a totally geodesic distribution by making the direct sum of the tangent space, tangent directions to the geodesics with the Euclidean factor. So these must always also be regarded as trivial examples. One can also do something similar by taking cones over surfaces in the Euclidean sphere, and then taking the product of an Euclidean factor. A more interesting class of examples are ruled hypersurfaces. These are hypersurfaces of Euclidean space that carry a smooth foliation by open subsets of affine subspaces. Of course, those rulings are totally geodesic in the Euclidean space, in particular also in the hypersurface. So these several families of trivial examples make us think that a classification theorem should be hard to get. But in fact, if you assume that the leaves of the totally geodesic foliation are complete, one can show that there are no further examples. So we must rule out the existence of what we call the surface-like strip. This means an open subset that is isometric to the product of a surface and an Euclidean factor. So if the hypersurface does not carry open subsets like this, and if the leaves are complete, this is an essential hypothesis here, then only ruled or partial tubes arise. Well, if you, if you want to get rid of those unpleasant assumptions, we can make just one that rules them all out, which is assuming the hypersurface to have positive ridge curvature. Then the hypersurface cannot be ruled, cannot have flat points, of course, neither ruled strips. So such a hypersurface must be a partial tube. So the only hypersurfaces with positive ridge curvature that carry a totally geodesic foliation of codimension 1. I forgot to mention that since we are dealing now with foliations with codimension 1, we need no requirement on integrability of the orthogonal distribution, which is automatic in this case, of course. So one may wonder if in the local case there arise other examples. And in fact, only one further class of examples occur, which are envelopes of one-parameter families of flat hypersurfaces. What I mean by the envelope of one-parameter family of hypersurface is this. We have a distribution of rank n-1 on the manifold with the property that the hypersurface is tangent to one of the members of the family along a leaf of this distribution. In the classical literature, this leaf along which this submanifold is tangent to the member of the family is called the characteristic of the family. And in our case, the leaves of the totally geodesic foliation are precisely characteristics of the one-parameter family of flat hypersurface that envelope F. So, going back to the statement, in the local case, a hypersurface that carries a totally geodesic foliation of codimension 1 must be either surface-like, which is those examples that are built from surfaces by taking products of Euclidean factors, or ruled, or a partial tube over a curve, but there can arise those examples that are envelopes of one-parameter families of flat hypersurfaces also. But in fact, in dimension 3, we can work a little bit harder to show that such envelopes already fit into one of the previous classes. So in dimension 3, locally, even locally, only the examples I have mentioned can arise. A three-dimensional hypersurface of Euclidean space, which carries a totally geodesic surface foliation in this case, must be either surface-like, ruled, or a partial tube over a curve. So now let us go to the detailed proofs of the results I've mentioned so far. Thank you. I must say that I learned this joke from Luis, so he's here. I must